So what are we presenting today? We're going to be focusing on detection of web browser heap corruption attacks. Moti and I, we both work in the area of malicious detection. I myself am in San Diego, he's in Tel Aviv. And a lot of this research went into a tool we call XMON. It's short for Exploitation Monitor. It fit in nicely with a larger part of our malicious web content detection network. And it's still in the research phase, and we're going to share today some of the research that went into it and some of the techniques that we found to be very useful in detection of heap corruption attacks as well as other types of attacks. One thing that we want to mention is that the talk is, I think we've changed the original title a little bit. It was defeating heap spray attacks. We wanted to make sure that we also include, heap corruption attacks. It's not strictly on heap spraying. But we're not going to be talking about exploitation protection measures such as DEP or safe exception handling, ASLR. The talk previous to ours was Alexander's talk on his heap lib library. Some of the background he gave is going to be repeated in this talk. So we hope you've seen his talk. It was an excellent talk.
Turn the mic so
Sure.
It's straight out in the face. Just let me show you. Like this so you can get it.
Excellent. All right, sorry about that. So we hope you've seen his talk. We're going to repeat a little bit of the information of some of the background on heap spraying and heap corruption, but it's only to reaffirm some of the understanding of what you know of heap corruption attacks. Even some of the talks I've seen at Black Hat today where heap spraying was mentioned, it seemed like some of the presenters got it and some of it didn't. It's a pretty simple technique, but we're going to go over some of it in hopefully a different manner than Alexander did, just so you can really understand it. So why are we presenting today? Basically, there's a large number of malicious sites on the internet. Client-side vulnerabilities and especially browser vulnerabilities are on the rise. IE7 has a lot of kind of protection mechanisms built within it, but we find a lot of people not keeping up with their patches, not using the latest version of their browsers. So it's constantly a problem. Attackers are focusing their efforts on the web. Heap corruption vulnerabilities are on the rise, and in the past 4 years, the exploit techniques have been very, very interesting. And for those who are researchers, it's very important to understand these techniques. The web is definitely a profit business, and there's multiple exploit toolkits readily available on the internet. It's good to understand these toolkits, which are all using heap corruption exploit techniques. MPAC, Web Attacker, IcePack. You've probably heard about these in the news constantly. If you're a web security researcher of some sort, you know these in great detail. MPAC recently is probably one of the most recent ones up there. Was used in a high-profile compromise of an Italian hosting provider. It was coined the Italian job by the media. In this particular case, over 10,000 sites were infected with this toolkit. The exploits that were hosted were all such that use the heap spray method. And it's heap spraying is literally across the board one of the most popular methods of heap corruption vulnerabilities. The stats are a little bit hard to see, but one important thing that I want for you to see is that a lot of people are not keeping up with patches. They have the latest browsers sometimes, but attackers are very successful in targeting users who aren't patching. The stats are shown a little bit here, and if you've ever seen the Web Attacker admin screen, you'll see that it's very successful as well on older, even 4 or 5 year ago kind of vulnerabilities. It's still very successful, even though the patch is available. So for those who've never been, dealt with web security, what do web browser exploits actually look like. At first glance, they look like any common web page. They don't have a I'm hacked kind of interface on them when you go see the web page. A recent example of this is the Miami Dolphins Super Bowl site. This site was compromised about 2 days before the Super Bowl. The labs, we discovered it in some of our scanning, and we looked at the source code. It actually had a hidden iframe in it that led to actually a few different vulnerabilities that switched over the course of a few days. This page right here doesn't look dangerous. You go to it, and otherwise you'd think everything's fine, but actually, if by visiting this page, you would have been exploited. To look at what malicious source code looks like a little bit here, this is using the heap spraying method. This is actually the set slice vulnerability. It's an iteration using the heap spray. It's also good to note that a lot of malicious authors are writing toolkits that include OS and browser detection. So you might think that you're using Firefox, and you go to a site and they're only going to be serving one exploit. That's generally not the case. Most sites you'll go to, and they're actually trying to detect your OS and your browser, and they'll match up your OS and your browser with a particular exploit that's going to be successful. In this particular case, it's looking for Vista, and it's looking that you're running IE7, and then it's going to serve you the VML exploit. Madi's going to take over and give you a little bit more insight into what this talk is going to be about.
Okay, so today we're going to talk about exploit that corrupt the heap, data on the heap to gain code execution, and about a way to detect this kind of exploit, which is the main point of our presentation today. So, why heap corruption? Mostly because attackers use heap corruption to exploit web browsers these days. We saw it with the VML, XML, create text range, and the set slice vulnerabilities. So, how attacker can corrupt the heap? Here we see one example, which is the VML case. Attacker wrote a VML script. Second. Back. So here we see one example, which is the VML case. Attacker wrote a VML script which eventually lead to the following assembly code. But the following assembly code suffers from what called an integer overflow, which basically let attacker later on override data on the heap more than he should. So we saw that how attacker can corrupt the heap. What's the big deal? Before 2004, not so much of a big deal. Most of this heap corruption classified as nothing more than a denial of service. But in 2004, it was a different story. Two guys named Blaze and Skyland show up with a way to exploit heap corruption in a more reliable way, which got the name heap spraying, which was to write a client-side scripting language which will spray the heap of the browser with an offsite and a shellcode. So that was in 2004. Why we care about it today? Because even today, 2007, we still see attackers exploit the VML set slice with the way that called heap spray, which is invented by Skyland and Blaze. Not only that, attackers wrote toolkits like IcePack, MPack that use the heap spray way to exploit web browsers. So, why it becomes so popular? Simple. One of the main reasons, it's very simple to use. All attacker need to do, spray the heap. Fill the memory of the browser with an offsite and shellcode. Step number 1. Step number 2, the attacker need to trigger the vulnerability, which will override data on the heap. And the last one, if an attacker need to redirect the execution to the shellcode. That's done, by corrupting a pointer that were on the heap. Now we will see a video that will paint us a better picture of this process. Here we see a block that represents the heap memory of the browsers. And now will join us a JavaScript code. In a second to join us. Now join us, which we see that when the browser executed, each loop basically allocated a chunk of buffer into the memory of the browsers, again and again. And if we will take a closer look into the content of the memories, we will find there that the attacker filled it with a NOP slide and a shellcode. So that was his first step. So now, attacker needs to trigger the vulnerability, which will overwrite data on the heap. Here we see a block of memory, heap header and heap data. And as we can see, attacker overwrite heap data with his own supply data. As we can see now, if we will take a closer look on what was the data before the corruption, we will see there that the attacker overwrite stuff like a virtual table pointers. So the attacker sprayed the heap and also triggered the vulnerability. Good for him. But now what? You need to redirect the execution, the flow of the module to the shellcode. How it's done? Attacker overwrite, corrupt the heap with his own content. He overwrite also a pointer such as a virtual table pointers. Now we will see that a video that will paint us a better picture of this process. Here we see a piece of code from the browser modules. As we can see, a pointer, a virtual function pointer being called. Since it got corrupted, instead of jumping to the real function, it executed the attacker's supplied code that was on the heap. So we saw how simple it's for the attacker to exploit heap corruption with the heap sprayway. It worked pretty well, but it's not perfect. Main two reasons for it is that if the machine had low memory and the attacker tried to spray the memory way too much, it will bring the machine to its knees. The second reason, when the attacker triggered the vulnerability, he didn't really set up the heap in a way that will make the exploitation more reliable. But there is no need to worry about it, because this year Alexander released a tool, JavaScript library called HeapLib, that take care of this stuff. I will not go into details on how we did it, because he did a talk before us and explained it in great details. But I will mention 2 points. There is no need to spray the heap anymore, and before triggering the vulnerability, attacker can set up the heap, which help make the exploitation much more reliable. So now the attacker have two ways to use: the heap spray way or Alexander way. How lovely. So we try to come up with a way to find out how to basically detect those kind of vulnerability if they use the heap spray way or the Alexander way. So there is one thing that's common to both of them, and it's basically the redirection point. So here we can see in this slide a format of a redirection pointer. And now we'll see where we see it more. Here is the XML case. As we can see here, a pointer redirects the execution to the attacker's supplied code. And here we see it again in the VML case. A pointer, a virtual function pointer, redirects the execution to the attacker's supply code. Not only here, we see it also here in the keyframe exploit. Here we see it again in the AD/ODB exploit. And the last one, exploit that was written with the Alexander library, and we see it again, it's depend in a pointer that will redirect the execution to the attacker's supplied shellcode.
were concerned with, I mean, Moti works in Tel Aviv and I'm in San Diego, is, you know, we're looking constantly at malicious data. We're constantly looking at all these exploits. And, you know, we're not really looking at a protection mechanism that can go into the compiler or, I mean, it could be going into a product, but what we were concerned with is a detection mechanism that we could build into multiple machines and look for a commonality between heap spraying, Alexander's method for his heap lib library. And as we were looking through and kind of debugging all the exploits, the commonality between all of them was pretty simple. It was constantly, you know, calling a virtual pointer and redirecting to the heap. It's a pretty simple concept, but we were like, well, let's play around with this and take it one step further and make a tool, you know, where we can take something kind of generic and detect these types of exploits. So basically that's what we did. We took the tool, and what the tool does is hook all the calls that follow the following format. The following format being a call to a virtual pointer. And when that call is actually executed, we check to see if the execution is being redirected, either directly or indirectly, to the heap. So as we said, we called this little tool XMON, exploitation monitor. What we were looking for was something that was generic in exploitation techniques that we had seen so far. We tested it on, you know, we deal with 80 to 90 million websites a day, and out of those, a huge magnitude of malicious websites. So we tested it on thousands of different exploits, and it was successful across all exploits. You know, but we wanted to work not on only specific exploits, but any new vulnerability that might come out. We don't want to keep on changing it. We wanted something that had minimal configuration. So XMON is going to actually be deployed, you know, internally across multiple machines. We wanted it to be something that was pretty easy and fit into our larger framework. We're talking today basically about heap corruption exploits, but XMON as well has other type of detection, exploit detection techniques within it. It has stack exploit detection and heap exploit detection techniques. One thing that we found pretty interesting is, okay, so it's detecting, you know, generically exploits, but we also sometimes, it would be nice to know if XMON could determine which vulnerability is actually being exploited. And what we found was that because that call to that virtual address it's not always the same, but in a lot of cases for vulnerabilities, the offset from the base DLL to that call is generally the same. We can figure out which vulnerability is actually being exploited. One nice thing too is we're also concerned if it's malicious or it's not malicious, but we'd also like to know if we had allowed it to execute, what would have happened. So we can dump the shellcode for offline analysis, or dump it into our automated machines that can kind of run it through, decode it if necessary, and figuring out what that exploit's attempting to do. The main concerns for XMON were speed and accuracy. So a little bit about the details of how XMON actually works. Right now, XMON is only injecting itself into Internet Explorer. XMON is a DLL we created, it's a module. And we're injecting ourselves into Internet Explorer. It could be across, it could be Firefox, it could be other browsers, but currently we're only using Internet Explorer. We've created some IDA plugins to basically go through all the DLLs, Internet Explorer, and generate a list of all the virtual calls. And when we start up IE with all the DLLs, we basically patch all those virtual calls. But we'd also like to patch DLLs that are getting dynamically loaded. The VML, for example, the VGX DLL doesn't get loaded. When IE starts, it's going to get loaded if it detects that there's VML code necessary in the JavaScript or in the HTML. So we also, patching is kind of an ongoing process. We do it dynamically as DLLs are being loaded. Just to give you an idea of the number of calls generally in some of these DLLs that we had to patch, the XML MS0661 vulnerability, which was an MS XML4 DLL, it had a total number of calls of around 2,000. Now, we wanted to try to be smart about which calls we actually patched. which calls we were actually patching. We didn't want to patch 2,000 calls. Although this is a research tool, we still try to focus on speed and performance. And so what we would determine is, well, we don't need to patch all the calls. We needed to patch calls that came from objects that are dynamically allocated. They're allocated on a heap. So, if you have C object, C equals new C object, that's going to be allocated on a heap. If it has any virtual functions, those are the virtual functions we care about. So we wrote some more IDA plugins, and we did a little bit more kind of runtime analysis. And it's still kind of in the research phase, but it's dramatically less calls than 2,000 calls that we're actually hooking. So how can we tell if execution is being redirected to the heap? There's a few different methods that we were playing around with, but page permissions is generally one. The heap in the stack process memory has a basic characteristics and layout. We can tell if it's getting redirected to the code section, to the stack, to the heap. And if it's getting redirected to the heap or the stack, generally there's no legitimate reason why that should be happening. And so that's definitely a trigger for malicious behavior. Content at that location is also an indication that something malicious is happening. In heap spraying especially, the content on the heap is going to be something, similar to what Alexander showed before with a 0C, 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 or 05, 05, 05, 05. Generally, it's going to be some type of NOP instructions that are also a legitimate heap address. So those are the two types of things you'll generally find, when doing a heap spray. Now, it's just the reality that a lot of exploits aren't written correctly, they're poorly written, and they crash. A lot of proof of concept code is like this. So what we wanted to do was also catch these type of exploits. So what we decided to do was hook the structured exception handler by hooking KUser exception. And this allowed us to basically catch any exception that was happening. Sometimes these were, exploits, and sometimes this was just the browser crashing. And then we dump it to our kind of, our machines that do automated analysis of what might happen. We might offload it to an analyst who will look at it in a little bit greater detail, see if it was actually an exploit, a 0-day of some sort, or if it was actually a known vulnerability. So when we're looking at any type of thing that we might have written, we're also looking at, well, how can we get around it? And potential limitations is something that we're constantly working with. I mean, as I said, we kind of tested all the exploits that, constantly, about 1,000 different exploits in 1,000 different ways that weren't at all similar to each other. They obviously use the same vulnerabilities at times, but they might have different shellcodes, different methods, either using the heap spray method or using Alexander's method. And the types of times when XMON might not be the most useful is when trying to detect malicious websites that actually aren't hosting exploits. And when that is basically, phishing website or potentially damaging software. The user might visit the website and be prompted to download an exe, and the user happily agrees. Well, this happens all the time. XMON isn't used for this specific purpose. We have other types of systems in place, like sandboxes that are going to, be able to indicate that this is malicious behavior. Another issue that we found was if, for example, in the Yahoo ActiveX control, we visited a site with XMON, and it was hosting a Yahoo ActiveX control exploit. The machine that XMON was on didn't have Yahoo ActiveX control installed. And so what actually happened was that it couldn't patch Yahoo ActiveX control and couldn't determine that the website was malicious. And playing around a little bit with exploits, what we determined as well is a lot of times you'll have the call that'll get redirected to the heap, or call that'll trampoline to the heap. And one thing that we played around was a call that redirected to a set of instructions that flowed for a little bit and then eventually led to the heap. So XMON tracks, some set of instructions that eventually jump to the heap, but there's a certain limit where it stops. The main point is that XMON isn't the solution to all kind of exploit websites, but we have multiple other types of systems in place that are going to catch these types of malicious websites. So detection in its depth is definitely something that we want to stress. In the grand scheme of things, how does XMON fit into our systems? So, to give you a little bit of insight of some of the technology that we have when we're scanning malicious websites, we have a multitude of different types of sandbox technologies. Generally visiting a website, allowing whatever behavior might happen, what might not happen to happen, and then figuring out how the state changed. We have reputation modules that basically look at what country is this malicious website hosted on, what are the links that are contained in the source, who owns the website, what hosting provider is it on, what are the relevant IP addresses that are around it, are they known to be malicious? Static detection modules, looking at signatures, and not only looking at exact signatures, but basically if that website might contain some type of polymorphic JavaScript, something like what Billy talked about today, decoding it and then matching against our signatures. And other type of modules, which basically where XMON fits in, as well as it kind of fits in those three other types of areas. So the types of systems we're talking about is kind of low interaction systems and high interaction systems. Low interactions are basically signature scanners that obviously aren't just looking for exact signatures. They do some decoding of JavaScript or some obfuscation on the pages, then match signatures. But these type of low interaction kind of systems have to take a lot of upkeep. You have to constantly come up with a new signature. They're looking for known exploits, known proof of concept code, generic methods sometimes for signatures, but kind of takes a lot of constant upkeep. The high interaction systems are sandboxes, basically. They're relatively slow. You constantly have to restart the state of the machine, and they detect malicious activity based on unauthorized modifications. A little bit of detail on the high interaction. So generally you start with a fresh machine state. You launch one single browser. You visit one URL at a time, and you allow for state modifications to happen. And you can only visit one URL at a time because you are monitoring the entire state of the machine. You compare the original state to the modified state, and you determine if it's malicious, suspicious, or benign. And this takes a lot of training sets. Is it known that this registry is commonly changed when I use visiting a web page, or this file is constantly changed? So in a high interaction honey client, it's constant. It's kind of a constant uptake, and also restarting the machine state is time consuming. So back to XMON. Where does it fit in? It's a hybrid model, basically, between low interaction and high interaction. We wanted some of both worlds. We wanted to increase the performance level, so we didn't want to be as slow as sandbox-type routines, but we wanted the speed to be quite fast. We wanted accurate detection of both known and unknown exploits. Generally, in the signature detection model, you're looking for known exploits. You're looking for known code that you've seen that's malicious. The behavior analysis system doesn't care what it's looking for as code. It's going to be looking for behavior that's generally not known to be benign. So with XMON, we were looking for known or unknown exploits. So it's a nice in-between. We wanted something that eliminated the need to monitor and restore the system's state and reduce the uncertainty. We really wanted something that was more accurate, that could determine, is it malicious or is it not malicious? So now with XMON, we can launch multiple browsers. We can launch multiple browsers because we're not monitoring the state of the machine. We're monitoring the internals of one browser. We're monitoring basically where the redirection is happening. We visit, each one of those browsers, visit URLs, and we disallow any change to the state. And while we visit the URL, as I said before, we're looking for the redirection. And when we can see that it actually redirects to the heap or the stack, or there's some other different methods that we didn't mention or we're not going to mention, we're focused on the heap here, we can tell if it's malicious or benign. So, I mean, XMON was a system that we put in place that we needed because it's real-time interaction where we visit websites. We're not only looking for signatures. We don't need to download the machine, let things run on the machine. This takes time, up to sometimes 90 seconds to see what's going on, what did the exploit actually do, monitor the state, constantly restart the machine. This was a really nice in-between. So one thing to also note is that XMON is not something that we determined to be the solution to everything. It's one thing that fit in nicely at the top of our layer to kind of filter in how should we proceed, basically. Does it trigger to the heap? If not, then we'll throw it to all our other systems. And the call technique is basically something that, Mati and I, we were discussing when he was in Tel Aviv, I was in San Diego. I was like, this is kind of cool. Let's add this. Let's see how it works. We played for a couple months with it, played with lots and lots of exploits, and it kept on having 100% kind of, or close to that kind of rate. And we're like, well, let's make a tool and let's throw it into our systems. And it seemed to be quite successful. So we kind of wanted to share that research with you. To play with. One thing that we might be doing is, at least for the research community, at some point, having an open interface where you can go and enter in a URL and determine if it's malicious or not. Obviously, this always begs attackers to go and put that URL so that they can see if our systems work or not. But XMON is meant to be a tool that we're constantly kind of playing with, the new exploit techniques, and changing on a constant basis. So. Is there any questions? I'm sorry, I can't hear you. You don't have to, but we chose to. We chose to, basically it was simple, 5 minutes to create a basic IDA plugin and go in and look at all the calls. Right, so when it's dynamically looking for DLLs? Right. All right. So what we've done is generally, we did a little bit of pre-research in that we took the entire system, scanned all the DLLs that were actually on that system, and generated the list for every single DLL. So that when that DLL actually loaded, we had that list ready to go. You have to run kind of that initialization. Is there any other questions?
You mentioned one potential pitfall would be changing the kind of jump and pointer call.
Yeah. It's not that we've seen this happen. It's that, we write a lot of exploits ourselves, and constantly we're just trying to see how can we get around our own systems. So we played around, and that's one way we would determine, well, when XMON's looking at the redirection, at one point does it say, okay, here's a call. If it goes right to the heap, that's malicious. If it goes call and then trampolines for a few instructions, that's malicious. But at what point does it actually stop? How many instructions do we actually monitor before it goes to the heap?
Would attackers using those techniques, would that potentially decrease the reliability of their exploits, or just simply make it, a few more instructions a little bit slower, not noticeable?
Yeah, I don't think it would.
It's not increase it.
Yeah, it wouldn't decrease it at all.
Can Microsoft do the same stuff
In the compiler? I was thinking, obviously we're thinking of these in terms of research tools. I know that, our company would always go, it's great if we could throw this into a product of some sort. Maybe. I think it's possible if for example, we're looking at, it's possible. But I definitely see this more as a research tool than something that would actually fit into a compiler or the OS. All right, if there's any more questions, find me after the talk, or else thank you very much.